Welcome to our deep dive into the mysteries of warp drive technology. Today we explore 30 years of warp drive. Is faster than light travel soon to be a reality? As we unravel decades of scientific ambition and futuristic breakthroughs, we'll discuss the evolution of warp drive theories, groundbreaking experiments, and the challenges facing interstellar travel. Stay tuned as we break down the story into 5 engaging segments that highlight pivotal moments in this quest for faster-than-light travel. In the early days of space exploration, scientists and visionaries dared to imagine a mode of travel that would bend the very fabric of space-time. The concept of warp drive emerged from theoretical physics, inspired by Einstein's equations and quantum mechanics. Early research laid the groundwork for challenging the speed of light barrier by hypothesizing that space itself could be manipulated. Over the past 30 years, dedicated researchers have worked on experimental models, testing miniaturized warp fields and energy manipulation techniques. This segment focuses on the initial breakthroughs and the pioneers who redefined the limits of possibility. Their relentless curiosity and innovative spirit sparked a journey of discovery that continues to fuel modern scientific endeavors. These early visions not only reimagined space travel, but also redefined our understanding of physics and the universe. As research advanced, several key experiments marked the evolution of warp drive theory. Laboratory tests, sophisticated simulations, and even small-scale field experiments have pushed the boundaries of what was once considered science fiction. Scientists developed prototypes to create controlled distortions in space-time, a concept that once belonged solely to the realm of imagination. This period was characterized by trial, error, and incremental progress that built a solid foundation for further innovation. These milestones reflect not just technological advances, but also a renewed hope for interstellar travel. Every experiment, successful or not, provided critical data, refining models and challenging prevailing theories. The collaborative efforts of international research teams have driven this momentum forward, inspiring both academic and private sectors to invest in the future of space exploration. Despite promising theories and exciting experiments, the practical engineering of a warp drive remains one of the most daunting challenges. The complexities of generating and controlling the required energy levels, along with maintaining stability in extreme conditions, are subjects of ongoing research. Engineers are tasked with designing systems that can withstand the immense forces associated with bending space-time. Innovations in material science and energy management are crucial to solving these technical puzzles. In this segment, we examine how modern engineers tackle issues such as heat dissipation, field containment, and power generation. Their work is not only a testament to human ingenuity, but also a critical step toward turning theoretical models into practical applications. Each challenge conquered brings us closer to the dream of interstellar travel and the possibility of a future where distances in space are no longer a barrier. The quest for a functional warp drive has united experts from diverse fields around the globe. Physicists, engineers, mathematicians, and even futurists are contributing their expertise to this ambitious endeavor. Collaborative research initiatives have led to shared knowledge, groundbreaking discoveries, and technological synergies that might not have been possible within isolated laboratories. International conferences, joint research projects, and open-source data initiatives have accelerated progress and inspired innovative approaches. This segment highlights the importance of teamwork and the fusion of ideas from various cultures and scientific traditions. The global partnership not only diversifies perspectives, but also pools resources and talent, ensuring that every breakthrough is built on a robust foundation of collective expertise. Such unity in the pursuit of knowledge is essential as we venture into uncharted cosmic territories. Looking forward, the path to achieving a practical warp drive continues to be paved with both promise and uncertainty. Future research is expected to address lingering theoretical questions while enhancing experimental designs. Emerging technologies in quantum computing and advanced materials could be the catalysts that push warp drive research into a new era. In this segment, we explore the potential impact of these innovations and the future milestones that researchers are aiming for. The dream of faster-than-light travel may soon transition from theoretical possibility to tangible reality, transforming how we perceive the cosmos. As new projects emerge and funding increases, the prospect of exploring distant galaxies becomes less a fantasy and more a strategic goal for future generations. The road ahead is challenging, but with continued innovation and global collaboration, the universe may soon be within our reach. One of the most crucial aspects of warp drive research is understanding how space-time can be manipulated. The Alcubierre Drive, a theoretical framework proposed in 1994, suggests that a spacecraft could travel faster than light by compressing space in front of it and expanding space behind it. Recent advances in physics have focused on whether this warp bubble can be generated under realistic conditions. Scientists are investigating ways to produce negative energy, a necessary component for stabilizing warp fields. Breakthroughs in quantum field theory and exotic matter research continue to push the boundaries of what we once believed possible. For warp drive technology to function, it requires exotic matter substances that possess negative energy density. However, no such material has been conclusively identified in nature. Physicists are exploring possible candidates, such as quantum vacuum fluctuations and dark energy, as potential sources. Advances in particle physics and high-energy experiments at facilities like CERN may eventually reveal methods to harness exotic matter. Although theoretical, the pursuit of this unknown form of energy is crucial for realizing the dream of interstellar travel. NASA's EagleWorks laboratory has been at the forefront of experimental warp drive research. Engineers and physicists have been testing small-scale warp field effects and analyzing possible energy sources. Dr. Harold White's research on warp bubble feasibility sparked global interest, leading to further investigations into how these concepts might be realized. While no concrete results have been achieved yet, the increasing investment in such studies signals a growing belief that faster-than-light travel could one day be attainable. Beyond governmental agencies like NASA, private companies and research organizations are also investing in warp drive studies. Enterprises like Blue Origin, SpaceX, and Breakthrough Starshot are exploring advanced propulsion systems that could pave the way for warp-related technologies. Crowd-funded research initiatives and academic partnerships have also contributed valuable insights. The involvement of the private sector adds momentum to the field, as commercial interest often accelerates technological progress. While the Alcubierre Drive remains the most well-known warp drive concept, alternative theories have also emerged. Some researchers have proposed the use of wormholes as shortcuts through space-time. Others have explored the concept of quantum tunneling, where particles can seemingly travel faster than light. Although these ideas remain speculative, they provide additional pathways for achieving interstellar travel beyond conventional propulsion methods. One of the biggest hurdles in warp drive research is the enormous energy requirement. Early estimates suggested that creating a warp bubble would require energy levels equivalent to the mass of Jupiter. Recent studies have refined these calculations, reducing the energy demand significantly, but it remains impractically high. Scientists are now looking into methods such as zero-point energy extraction and quantum field manipulation to make warp travel more feasible. If humanity were to achieve warp drive technology, ethical concerns would inevitably arise. How would we regulate interstellar travel? Would faster-than-light capability be restricted to government use, or would it be available to the public? Additionally, the potential consequences of interacting with extraterrestrial civilizations must be considered. Responsible exploration and ethical frameworks must be developed alongside technological advancements to ensure a safe and fair future. Physicists have been working on refining the mathematical models supporting warp drive concepts. The Einstein field equations, modified with exotic matter components, have provided deeper insights into space-time distortions. Researchers have also employed advanced simulations to test how space-time reacts under different energy conditions. Continued refinements in theoretical physics will be essential to bridging the gap between mathematical models and experimental validation. AI and machine learning have become invaluable tools in analyzing complex space-time equations and optimizing warp drive simulations. These technologies help scientists identify patterns, streamline calculations, and simulate warp field interactions with unprecedented accuracy. AI-driven advancements may accelerate the discovery of practical solutions for faster-than-light travel. Warp drive technology, if realized, could revolutionize more than just space travel. The ability to manipulate space-time could lead to breakthroughs in quantum computing, energy production, and even medical advancements. Understanding warp fields may unlock new ways to generate and store energy, leading to a paradigm shift in how we harness power. Some physicists have proposed links between quantum entanglement and space-time warping. While quantum entanglement does not allow for faster-than-light communication, its underlying principles might offer insights into how space-time could be manipulated on a macroscopic scale. Research in quantum mechanics continues to provide unexpected findings that could influence warp drive development. Although we do not yet have physical warp drives, scientists have proposed theoretical prototypes that could one day be built. These designs include small-scale warp field generators and modular spacecraft concepts that incorporate space-time manipulation mechanisms. Testing these prototypes in controlled environments may be a crucial step toward validating the feasibility of warp travel. Dark energy, the mysterious force driving the accelerated expansion of the universe, could play a significant role in warp drive physics. Some theories suggest that harnessing dark energy could provide the negative energy required for a warp bubble. Ongoing cosmological studies may eventually reveal whether dark energy is a viable power source for faster-than-light travel. The concept of warp drive has captivated the public imagination for decades, thanks in part to science fiction. Movies, books, and TV shows like Star Trek have shaped how people perceive faster-than-light travel. Public interest in the topic has fueled funding and academic interest, demonstrating how cultural enthusiasm can drive scientific progress. If warp drive technology were to become reality, where would we go first? Scientists have identified several exoplanets that could be prime targets for interstellar missions. Proxima Centauri b, TRAPPIST-1 planets, and other potentially habitable worlds could be within humanity's reach within decades rather than millennia. One of the fascinating consequences of faster-than-light travel is its potential impact on time dilation. While traditional relativity predicts that approaching light speed slows time for travelers, a warp bubble could bypass this limitation. Understanding how time behaves within a warp field remains an active area of research. Various defense organizations have expressed interest in advanced propulsion technologies, including warp drives. Military applications could range from rapid response capabilities to deep space surveillance. While controversial, government investment in warp research could provide significant funding and technological advancements. Every technological advancement comes with risks, and warp drive is no exception. Unintended space-time distortions could have unforeseen consequences, including gravitational anomalies or disruptions to planetary orbits. Researchers must assess and mitigate these risks before warp travel becomes a reality. Even if warp drive proves to be unfeasible, alternative propulsion methods such as nuclear fusion rockets, antimatter propulsion, and solar sails may still allow humanity to explore the stars. Understanding warp physics can still contribute valuable insights to the broader field of advanced propulsion. The road to practical warp drive technology is long, but each discovery brings us closer. Upcoming research efforts will focus on refining energy models, testing small-scale warp field generators, and continuing the search for exotic matter. With persistence and innovation, the dream of faster-than-light travel may one day become reality. One of the biggest challenges in warp drive research is integrating quantum mechanics with general relativity. While Einstein's theory of general relativity describes gravity on large scales, quantum mechanics governs the microscopic world. A successful quantum gravity theory, such as string theory or loop quantum gravity, could reveal how space-time manipulation is possible on a practical level. Scientists are actively researching whether quantum fluctuations could generate a stable warp bubble, which would be a game-changing discovery for interstellar travel. Even if we could generate a warp bubble, how would a spacecraft control its movement? Traditional navigation relies on sensors, star maps, and communication with Earth, but traveling faster than light presents new challenges. Light from distant objects may appear distorted, making traditional star tracking methods unreliable. Scientists are exploring quantum positioning systems and alternative methods of interstellar navigation that could function in a warped space-time environment. Black holes naturally bend space-time, and studying them could provide insights into how warp fields might function. Scientists have discovered that spinning black holes create frame-dragging effects, which could be mimicked in artificial warp fields. If we understand how extreme gravitational forces shape the universe, we may learn how to replicate similar effects in a controlled manner to create a functional warp drive. With current technology, scientists can't yet build a working warp drive, but they can simulate one. Supercomputers and advanced physics simulations have been used to model how warp bubbles could behave under various conditions. These simulations help refine energy requirements, test stability theories, and guide future laboratory experiments. Some researchers have proposed starting with a small-scale warp drive experiment rather than attempting a full-sized spacecraft. The idea would be to create tiny distortions in space-time in a controlled lab setting using electromagnetic fields or quantum effects. If successful, such experiments could confirm that warping space is possible, even at a microscopic level. Scientists have speculated that natural warp fields might exist in the universe. If space-time can be bent artificially, then perhaps there are already natural occurrences of this phenomenon. Observing gravitational lensing, cosmic strings, or unusual anomalies in space could provide clues that warp-like effects are occurring naturally. If we could find and study such a phenomenon, it might accelerate our understanding of warp technology. Dark matter remains one of the biggest mysteries in physics. If it interacts with gravity in an unusual way, it could provide insights into space-time manipulation. Some researchers suggest that dark matter could hold the key to stabilizing a warp bubble or reducing the energy required to achieve one. Understanding the properties of dark matter could be essential to making warp travel a reality. String theory proposes that the universe is made of tiny vibrating strings that dictate the nature of space-time. Some versions of string theory predict extra dimensions beyond the three we experience. If these extra dimensions exist, they might provide new ways to warp space-time and open pathways for faster-than-light travel. Scientists are currently testing string theory's predictions through particle physics and cosmology. The original Alcubierre warp drive concept has inspired numerous variations, each attempting to improve energy efficiency or address stability concerns. Some versions propose using different types of exotic matter, while others suggest alternative geometries for the warp bubble. Researchers are constantly refining the original model to make it more practical for real-world application. If warp drive technology becomes a reality, the consequences would be profound. Humanity would no longer be confined to the solar system, and new civilizations could be encountered. The political, social, and economic effects of interstellar expansion would be as transformative as the discovery of the New World in the age of exploration. Entire new industries would emerge around space colonization, planetary mining, and deep space travel. While warp drive remains theoretical, some small-scale experiments have been proposed to test warp-like effects. NASA's EagleWorks Lab and other research institutions are exploring methods to detect tiny distortions in space-time. If a controlled warp effect could be demonstrated in a lab, it would be a historic milestone in propulsion science. If faster-than-light travel becomes reality, piloting a warp-capable spacecraft would be incredibly complex. Human reaction times may be too slow to adjust to space-time distortions, meaning artificial intelligence, AI would likely be required for navigation and system management. AI-powered onboard computers could make real-time calculations to ensure smooth and precise travel through warped space. Even with warp technology, some journeys might take years or decades. Cryogenic sleep or stasis technology could be essential for preserving crew members on long-duration missions. Research into suspended animation and biological preservation is ongoing, with potential applications for interstellar travel. If we can manipulate space-time for travel, could we also use warp fields to enhance communication? Faster-than-light travel could enable near-instantaneous communication between distant planets. Developing such technology would revolutionize interstellar missions, enabling real-time contact between Earth and deep space explorers. Some physicists have proposed that the entire universe might function like a giant warp drive, expanding space at speeds faster than light. If we can understand the mechanics of cosmic expansion, we might learn how to replicate similar effects on a smaller scale for space travel. The ability to travel faster than light would transform our civilization on every level. A warp-capable society might see new forms of government, new economic systems, and even cultural shifts as humans become an interstellar species. The possibilities are endless, and future generations may live in a world where interplanetary travel is as common as air travel today. If warp drive becomes feasible, we could explore exoplanets at an unprecedented rate.